So only way how you can model this noise is using statistics. So statistics, we have two things. One is called as mean square. Another one is called as root mean square. Another one is called as variance. So you have all these formulas in probability by which you can model this noise. So there are several textbooks which model noise with several mechanisms. So one such method is using a mean square. One is using a root mean square. One will use only the mean. Some may use the variance. So definitely all are different models aimed at getting an exact value for the thermal noise. And as the name indicates, this thermal noise will have a strong dependence on temperature, and it is proportional to T. So as your temperature is going to rise, the thermal noise power which is available inside the source is also going to be rising. The thermal noise power is given by, see the equation, PNA equal to KT delta F. So it is the available noise power. So P refers to power, N refers to noise, A refers to available noise power. See, this power is actually the power generated because of movement of electrons inside the resistance under a constant temperature. So this power will be added to your actual signal flowing through your resistance. So that is where noise enters slowly inside your circuit. So you can see in the expression KT delta F. K is your Boltzmann constant. You know this is the constant value 1.38 10 power minus 23. It is minus 23 joules per Kelvin. T is the temperature in Kelvin, and delta F is the noise bandwidth. See, all expressions for noise will have this bandwidth term coming, because it is very evident that if the bandwidth is large, noise is also going to be large. If the circuit is going to have a very, very narrow bandwidth, then the noise is going to be very, very less. See, it is very simple. If you are having a mall and the entrance is very wide, more people will enter. So more people, more crowd, more noise. But at the same time, the mall is having going to have only one entrance for exit and one entrance for entry, means definitely people will be allowed only in queue. So definitely you can restrict the amount of people entering the mall, right? So in that way, I can control the amount of people, less crowd, less noise. See, everything comes from nature only. So the bandwidth is more, the noise is more. The bandwidth is less, the noise is less. And that is verified by this equation. So you see here, P is proportional to two terms. P is proportional to T, temperature, and P is proportional to delta F. Delta S is going to be, it is not your normal bandwidth, it is called as noise bandwidth. And we will clearly define what is delta F in the upcoming slides. So this equation tells that the available noise power has a spectral density which is independent of frequency. And you can see in the previous equation, there is no term involving F. Bandwidth means it is a constant value. It does not depend on F. So it does not have any term depending on frequency. So we can say this noise power is independent of frequency. Or I can say this noise affects all the frequencies uniformly. It does not show any partiality. It is going to affect all the frequencies uniformly. Okay. So any receiver or any amplifier which is going to operate will definitely have a thermal noise component, because it is going to affect all the frequencies uniformly. Or I can say spectral density is independent of frequency. The noise power expression does not have a term F. Instead, it is having a term delta F. The delta F is called as the noise power, noise bandwidth of the component, whatever we are going to use.